Alright, hey guys, welcome back to Unit 4, Work and Energy Part 2. We learned last time, we defined this quantity called work, and it was equal to the force on an object dot the distance it travels during that force in the direction of the distance. Or we would say the force times the distance times the cosine of theta between it's the vector between the force and the distance. So if that's my force there, that's my distance vector there. Theta is the angle between them, like that. And through the magic of physics formulas and setting force equal to mass times acceleration, and using a formula for Vf squared equals Vi squared plus 2AD, we ended up getting that the work was equal to the change in the kinetic energy of that object. And that was just EK final minus EK initial, like that, which EK we derived as Vf squared. So 1/2 mv squared. So 1/2 mvf squared subtract 1/2 mvi squared, like that. So that was the work done on an object to increase its speed. So let's look at an example of that and fill in the picture a little bit more here. If this was my ground, let's say, and let's say I have a 5 kilogram mass up here, and it is 10 meters above the ground. Let's figure out what the energy is on that object, how much work is done on that object by the Earth's gravity, right? That's what would be pulling it down. In questions that are up and down, it's usually gravity that's giving us the work, supplying it. If it's a question with like humans in it, then they're usually giving us the energy. So what is the initial velocity of that block? It's 0. The final velocity we don't know. We do know the acceleration is 9.8 meters per second squared, down, right? I'll just say everything down is positive. And we're going to move down delta D. I'll put a delta in there. We're going to move down 10 meters, right? So I'll keep that as positive as well. But get my little axis here. There's my axis in whatever direction. I'll just say it's the y direction. So, there's a pen. So there's 10 meters there. So if I want to find the final velocity, it's just this formula here. It's a nice 2D formula, 2a times the change in the distance. Not a huge fan of those deltas at the beginning of the course, but I'm going to start adding them now for this part. And so Vf will equal Vi is 0. So it's just going to be 2a times the change in distance, all square rooted like that. And I know those numbers. 2 times 9.8 on my calculator times 10. Square root that. This actually works out to be a nice number, which is no fluke, because I designed the question. So this thing, when it hits the ground, is going 14 meters per second, like the instant before it hits the ground. Okay, so what is the work done on this object? What is the change in the kinetic energy of this object? It is just 1/2 times m times Vf squared minus 1/2 m times Vi squared, which is going to equal 1/2 times 5 times 14 squared. Subtract 0. There's no initial velocity here, so this term is 0. And that is going to equal 490 joules of energy. that gravity added to that box. Okay, so we need to reconcile something which says that there's a law in physics where it says you can't get energy out of nothing. You can't create energy. You can't destroy energy. There has to be this balance of energy in nature, or else, we would get free energy in everything we do. So in the initial situation in this question, initially, we have this box up in the air, right? And it has this kinetic energy equal to 0. And then in the final situation, the box is now on the ground, and or just the instant before it hits the ground. Obviously, if it hits the ground, it's going to stop, and there'll be all kinds of mathematical things we won't be able to calculate. So in this class, we always just kind of look at the instant before it hits the ground. Everything after that is very hard to solve, and there's lots of, you have to use a computer to solve what would happen, after this thing hit the ground. Would it bounce, depending on, some sort of friction forces and how bouncy the things are and all that. So we're going to stay away from that for now. So just looking at the final energy and the initial energy, they are not equal. So we're going to have to add some other term here. And I'll just put a P for now. And we're going to have to add some other term here. And I'll put a P as well, so that initially the energy, we want this statement to be true. We want the initial energy of our box to equal its final energy, right? This is called conservation of energy. Conservation of energy. And it says in physics, you can't create energy, you can't destroy energy. If you do an experiment, all your energy has to be accounted for. So if I start with 0 and I end up with 490, I haven't accounted for everything. So I'm adding these two terms in, an initial P and an initial, or a final P as well. Okay, and if you look in this question, the initial P will have to equal, well, one thing they could be anything, right? As long as it balances, and I'll put 0 joules here. So does that work? Does the total initial energy equal, it equals 490, and the final initial energy equals 490. So that checks off that box. Now, if I pick a different color, pick a cool color here. I already did green, so I'll do purple. Let's say instead I let this equal, I don't know, whatever number I want, 1,000 joules, right? If the initial potential energy equals 1,000 joules, then my total energy will equal 1,000 joules. And so here I would have to say that this equals 510. And then the EKF plus the EPF would equal 1,000. Okay, so that would check off that box. So that's what I mean when I say potential energies, they can have whatever values you set. It depends on where you set your axis in your system. But you get to choose your axis, and the math will still all balance out. It's kind of like in those questions that we did with projectile motion, where you start off the cliff. You could set the cliff to its height of, let's say it was 15 meters, and set the ground to 0, or you could set the cliff to 0 and the ground to minus 15 meters. It doesn't matter. The math will all work out the same, as long as you're consistent about your units. Okay. So this is what we have here. We have this potential energy now. Get this pen. And that's what the EP stands for. So I grab my pen here, and I'll say that EI equals EKI plus EPI, and EF equals EKF plus EPF. So let's define what this potential energy is. Right, this EP, okay? It's going to be different depending on the question you have. But most of our questions involve gravity. You've seen gravity in grade 11 questions as well, so I'm sure you've seen this EP, which we call potential energy. Okay, and let's look at it. Let's look at, maybe we'll look at the work involved in moving an object. Here's my ground again. And let's say I want to move an object up a distance d, or actually h, I think is what the book uses most often. So I will draw a height of h here, and I want to move some object of mass m up through the Earth's gravity. Well, what is the work done on that object to get it up there? It's just equal times the force dot the distance. The force is just mg, right? Mass times gravity. And the distance is this change in height that's going to occur when I move it up. And that's what we actually call potential energy. And I'll show you why we get potential energy out of that. So first thing I just want to add here is a negative sign, because the distance I'm moving it is up, but the force of gravity is down. So that's where that negative sign comes in, because this is actually a theta of 180 degrees. There's my force vector g. There's my change in height vector. Change in height vector delta h. Okay. So that is the work required. And let's look at this formula that we just created back over here, which said that EI equals EF, conservation of energy. This said that EKI plus EPI equals EKF plus EPF. I'm just going to rearrange this so that I get EKF on this side. I'll bring this over here, so this will be subtract EKI, and then I'll be left with EPI on this side and EPF on that side. Check my algebra, I think it's right. This is the change in kinetic energy, and this is the negative change in potential energy. All right, so I'm saying that when I have a change in kinetic energy, it affects my potential energy change, but negatively. Does that work out for us? Because I said that this was work, right? So this is work, right? And is our negative potential energy also our work? Yes, our potential energy we're going to say is mg delta h. And so if I say that this is, if the change in potential energy is mg times the change in height, then this means that work equals negative times the negative of mgh, which is also our work. So work equals work, and it all works out. But only if I define this potential energy as mg delta h. Okay, so here's what I have then. I have that if I want to look at this as a formula, let's look at this initial question that we had, okay? Where I was on the ground, yes, and I wanted to find out how fast this thing, this 5 kilogram mass, was going to hit the ground at. And this was 10 meters up. Now I had to do some kinematic stuff to get that. I had to find the final velocity using some kinematics equations, and And now I want to see if there's a shortcut. So I am going to say that the initial energy is equal to final energy, right? The initial energy for me always is the initial kinetic energy plus the um, initial potential energy, and that will equal the final kinetic energy plus the final potential energy. There's a lot of subscripts in here. It gets kind of annoying. But luckily, a lot of times things will cancel out. So what's the initial kinetic energy of this box? It's 0. It's not moving. What's the initial potential energy of this box? It is mg times the change in height, right? Which is 10 meters. What is the final kinetic energy? That's what I'm looking for. So it's 1/2 mvf squared. And what's the potential final potential energy? It is 0 because the thing is on the ground, so the change in height is 0. So when I go to solve this problem now, there's no vectors anymore, which is nice. I end up getting 5 times 9.8, and the masses will actually cancel here too, but I'm not going to do that for now. 5 times 9.8 times 10 equals 1/2 times 5 times VF squared. Can I solve for VF? Let's do it. It's going to equal, well, the 5's do cancel, so why don't we just get rid of them? It's going to equal 2 times 9.8 times 10 square rooted. 2 times 9.8 times 10 square rooted. Great. So the final answer is 14 meters per second. And that's the answer I got in the first problem as well. It's just nice to not have to use kinematics anymore and just use energy equations. Let's look at another cool example of using energy instead of all these kinematics equations. Notice there's no time in that question at all, which is nice as well, right? Okay, so here's an example. A person swings from a 6-meter platform on some sort of rope, right, to a 9-meter platform. If they stop on the 9-meter platform, how fast do they need to launch from the 6-meter platform? So it's a Tarzan swing. And let me draw you a picture of that. There is a 6-meter platform up here. There is our dude. He is on some sort of rope, and he has got to get up to this platform and come to a stop. So he's going to end up being here when the question is done. Not very realistic. My rope should probably be higher, whatever. Doesn't matter. Also, this guy was swinging an arc, right? So kinematics is kind of, we can't use that. There's just too much complication going on. The movement in the X and the Y is like they're functions of one another. No one's moving in a straight line. There's going to be obviously some acceleration changes, force of gravity the whole time, all that stuff. So that question would be really, really tricky to do if we were going to solve for time, acceleration, all the velocities, initial final velocities, distances. We don't want any of that stuff. What we want to do is we want to say that the initial energy of this person will have to equal the final energy of this person. We're not considering that they're losing any energy in this process, even though they would through the rope and air resistance and all that. So his initial kinetic energy plus his initial potential energy will have to equal his final kinetic energy plus his final potential energy, like that. What is the initial kinetic energy? That's what we're looking to solve. We don't know that initial speed, right? Notice I didn't give you the mass of this person either, but let's see why we don't need it. What's the initial potential energy of the person? Well, I'm going to set my ground, obviously, to 0 meters, so that my change in heights are just the heights of the platform. Right? I don't need to do that. I could set like one of the platform. I could set this platform to 0 and this one to 3 because it's up 3. It wouldn't make the math any different. It's a completely linear equation here, so that would be fine to do. I'm not going to do that. I'm just going to say that this is mg times 6, because that's where that platform is. What's the final kinetic energy? That's 0. What is the final potential energy? mg times 9. And we could see that the m's cancel out, which is nice for us. And I'm just going to move stuff over to the other side here. 1/2 vi squared, and that's going to equal 9g subtract 6g. 9g, that is not a g. Fix that. Subtract 6g. And that's where the 3 came from anyways. So if I would have let my platform equal 0 here and 3 here, I still would have got 3g. vi squared, and that is 3g. So my initial velocity will just equal the square root of 6g. Maybe you could work out the math of that. It is going to be 3 times 2 times 9.8 square rooted. So 7.67. 7.7 meters per second. Not bad. So you take this incredibly complex question, and if you're just looking for velocities, you turn it into a super simple question where mass doesn't even matter. Okay, so that is the glory of solving for initial energy equals final energy. Just knowing that a potential energy due to gravity on an object is just its mass times its gravity times how much you change the height of that object. Okay, so we kind of contrive that so that we're not gaining or losing any energy in our questions, and it makes all of our questions work out nicely. We'll learn in the next time we talk about the potential energy from springs as well, where it can just add a little bit more complexity to the questions, because these actually are quite easy to do, and it's hard to really throw any kind of question like this that would be difficult for you to do. Okay, so yeah, stay tuned for that next week, and I'll post some questions on the Google Classroom for you to try as well on potential energy, kinetic energy, and conservation of energy. Thanks. Talk to you soon.